Welcome to this guest lecture on image generation using generative AI. My name is Pranav Durai and I am a research fellow at Stanford University School of Medicine. And thank you very much for joining me today over here to spend your valuable time with me to learn a little bit about generative AI and how we can kind of use this technology to generate images. Right? So we use this as kind of like a one-on-one foundational, let's say, course to kind of understand the different capabilities of generative AI specifically for image generation. Okay. So what I have for today is the agenda over here. We'll first start with an overview of image processing. So we'll try to understand what exactly can we do with just raw images and how we can kind of extract meaningful data from the images. And then we'll also kind of have an introduction to generative AI specifically for images, right? So we'll try to understand different capabilities, different models, and all of that. And so we'll also explore a few different image generation models. So over these years, there's a lot of advancements in generative AI-based models itself. So we'll kind of explore all of these models and see how they've evolved in all of these years and try to understand where we are at right now. Okay, and then we'll also kind of see some different use cases, and we'll kind of explore this concept called image reconstruction using generative AI and different techniques that we can use to do that. And we kind of wrap it up with talking about a little bit of ethical considerations because the shiny and most powerful tech is not always something that is safe, right? So we'll kind of discuss a few ethical considerations as well. Right? So does that sound interesting?
Yes.
Okay, cool. Alright, so before we dive deeper into today's talk itself, I'll kind of show off what we've been doing at Stanford. So my work at Stanford is basically on early detection of cancer cells in PET-CT imaging, right? So we know for a fact that if you diagnose cancer after, let's say, stage 3, it's really hard to save the patient, right? So there are a lot of treatments like chemotherapy and radiation therapy, and then all of these hospitals, they say that, hey, we have a cancer survivor because they went through this chemotherapy in our hospital. But then the problem is the cancer cells, they come back, right? So now the fact is it's changing a little bit because it's not 100% survival, right? Because if it comes back, then the patient has to go through the treatment on again, right? So how can we do early detection in, let's say, stage 1 and stage 2 itself, so that we can kill the cells really early in the life cycle and then prevent it completely to save the patient, right? So we initially started with developing antibodies for different types of cancers, and what we do is we introduce that cancer into lab rats, right? So what you see over here is not human beings, but lab rats over here, right? So there are 4 rats, and this is like a bed-like structure which holds all of these 4 mice. They're kind of sedated so that they don't move. And then you do like a complete vertical PET-CT scan of that structure, and then you do segmentation of it, right? So what you can do is, you can do organ segmentation, trying to segment out different organs in that 3D volume. And not just that, but also try to identify the cancer cells in that specific organ, right? And then what you can do is, you can do kind of like a prognosis study of this, because after you inject that cancer into that specific organ, you do an initial scan, and then after that, you introduce the antibody into that same organ, and then you monitor this scan for a period of, let's say, a couple of days, And then you notice that, hey, are the cells dying or not? Right? So then you know that, hey, this antibody actually helped to solve some problem. So the phase 1 of the work that we did was published in WMIC 2024 in Montreal, Canada. So WMIC stands for World Molecular Imaging Congress, and folks from really big Ivy Leagues, from Harvard, from Yale, all of them, they come to present their work at WMIC, and this is the publication. Alright, so a question to the audience over here: what is image processing? You can probably raise your hand. Anyone? How would you define image processing? Well, it can be a wrong answer. Anyone wants to try? How do you define image processing? So I actually have an equation for this, which makes this concept really simple for anyone to understand. Right? So I say that image processing is nothing but manipulation of pixels. So we know that images are made of pixels, right? So you manipulate these images to get really important or useful data from the image itself. Right? And then you also do a little bit of analysis. Right? So after you extract data from, let's say, the raw image data, right? You can do a lot of these analysis based on different capabilities that you want to use, right? So this is how you would do it. But then the question is, what can you do with image processing, right? What are the capabilities that I spoke about? So the first thing, which is kind of like a ninth capability of image processing, is nothing but image enhancement. And if so all of you are on Instagram these days, so before posting something, you edit your image, right? So that is nothing but image enhancement. And when you edit an image, there are different types of parameters that you can control, right? So you have your brightness and contrast, which kind of changes the exposure and darkness of that image. You have sharpness, which introduces more clarity into the raw data. The raw data is nothing but the image itself that you have, right? Saturation is nothing but you introduce more colors. You kind of play around with the vibrance of colors that you have in your image. Right? And then you also have highlights and shadows. Right? So highlights are nothing but the brightest part of your image, and shadows are the darkest part of your image. Right? And that is how you kind of control. And then you also have these LUTs. Right? So LUTs are nothing but lookup tables. Right? So what you have over here is a before image. Right? And then the after image looks like it was taken out of a movie. Right? It kind of has like a cinematic feel to it. So what you do is you map some pixels to a different pixel value, so that you get a really good color scheme over here, which looks cinematic. Right? And then you can do that using lookup tables. And an example of lookup table is the filters that you have on social media platforms. Right? So different filters, they give you different look. Right? And then you choose the best filter for your image before you post it. So that's an example of lookup. Right? So a little bit of fundamentals over here. So we know that there are a lot of these images that we keep capturing every single day. But then how does the computer system interpret this image? Right? So images appear as pixels. Right? So each individual component you see over here is a pixel. Right? And they are digitally represented as two-dimensional matrices. Right? So what you can see over here is that you have pixel values for each of the pixels that you have in the image. Right? So you can see that This is a grayscale image, right? So you also have black pixels and you have white pixels, right? But in between these two pixels, you also have gray pixels, right? So it's kind of like a range that you see over here. So the pixel range for any two-dimensional matrix is from 0 to 255, right? So 0 actually represents the most darkest pixel, right? So if you see over here, this pixel is very dark, and if you see the corresponding value, it's 0 over here, right? And on the other hand, let's say this pixel is completely white, and if you see the corresponding value for that, it's 255, right? So that's how all of these pixels are represented, and it's represented as a matrix, right? Two-dimensional matrix. This is another capability using image processing, right? So image visualization, right? I'm pretty sure that in your homes you would have pictures of your grandparents, right? And all of these photographs, they've gone through all of these years of being stored in, let's say, an antique box. So all of these artifacts started appearing on the image, right? So it's kind of cracked up, it's folded, it's not stored properly, right? And it's really hard to kind of use it in this generation. Right? So you can do a lot of these techniques. So you have noise removal, which kind of removes noise artifacts from the image. You also have blur removal, right? So if you have parts of an image which are slightly blurred out, you can remove that using these techniques. You can also have artifact cleanup. So all of these crumbles that you see over here in the photo are artifacts, and you can kind of remove all of these artifacts and get a very smooth, seamless image over here. Right? And then you can also do colorization. Right? So most of these images that were shot, let's say 50 or 60 years ago, was shot in black and white. Right? And now we have the tech to kind of colorize those images. Right? So you can convert black and white images into color images, and this can be done using image processing. Alright, so we shoot a lot of these images, right? But they take up a lot of storage, right? So image compression is also another technique that we have, where you can kind of play around with the size of the image in terms of how big it is, based on different formats, right? So for example, if you shoot or if you capture an image using a professional DSLR, then it's shot in .RAW. So it's like a raw format. So basically directly the data from the CMOS sensor that you have in your DSLR camera. But then what happens is you can't directly share those raw images because they're really large. So probably 30, 50 megapixels in size. So what you do is you compress them in a shareable format like JPEG or PNG, so that it becomes much easier to share it in different platforms, also for storing it. Right? So you have a lot of these compression algorithms. Okay, so another thing that I wanted to talk about is actually image stitching, right? So you probably have this feature in your smartphone, right? So you take the smartphone and then you pan around, and then you get a really high resolution image of, let's say, a landscape that you want to capture. So how does this thing work, right? So what it does is that when you pan your camera, when you pan your smartphone, you take multiple images, right? So these are the images. So what you do is you do key point detection. Right? So let's take this image and this image. So there are some key points over here and some key points over here. So you match the features over here. Right? So you match it so that you can completely align those two patches in your panorama to get really good stitching. Right? And then what you do is you also do transformation. Right? So there is a native warping kind of an effect because you're panning your camera. So you kind of estimate that warp and you handle for it, right? You solve for it so that you get a complete, blended image, right? So I'll just show you the process in real time. Right? And then you get this image. And now you notice that there are a lot of these, let's say, steps that you need to do to get a stitched image. But all of this happens natively in your smartphone because it's so powerful right now. Because the SoCs are capable of handling all of those large processing tasks. So it's very seamless when you use it for the first time on your smartphone. All right. So the next thing is a little bit of deep learning, right? So this is something called image recognition or image classification, right? So just a basic thing. I give an input image of, let's say, a cat or a dog to this algorithm. I kind of forward pass it through the algorithm, and then the algorithm has to say whether it's a cat or a dog, right? Or whatever is forward passed through that algorithm. So what you can see over here is labeled, photos over here, and you have multiple, layers in the neural network itself that learns all of these visual characteristics from the input data that you have, and it kind of learns to predict what is present in that image. Right? So it's kind of like a supervised learning approach or technique that you can see over here. So visual characteristics tries to learn the different visual characteristics from the images, and then it identifies what exactly is the subject based on the characteristics, and then you can do this using deep learning techniques. Right. So this is just an introduction to what we can do using just image processing. So just the classical techniques that the industry has been using so far to solve really large image processing problems. And now we'll talk about generative AI. Right? So I also have an equation for this. So a generative model is nothing but it learns the underlying patterns from the data that you pass it as an input, right? And using those patterns, it learns to produce new data, right? So it kind of, learns patterns from the data that you pass as an input. So image, for example, for image generation-based models, it learns the visual characteristics of the images that you pass as an input. And then using that, it learns to generate new data which it was not trained on, right? So let's have a look into that. And I'll actually start with this model called the VAE, or the variational autoencoder, right? And this was first introduced in 2013, right? So basically, this is kind of like a encoder-decoder style architecture, right? So what it does is that the encoder, it maps the image's features into a lower dimensional or a lower resolution latent space, right? And using that, it kind of learns the probabilistic distribution of those details, right? And then in the end, you have a decoder as part of the architecture, which reconstructs that image based on the latent space that you have. Right? So what you can see is over here, it's trying to generate handwritten text, and this is from this data set called MNIST, M-N-I-S-T. It's like the hello world of computer vision, right? So you have all of these digits over here, which it learns to generate from randomness. Right? But you can see that in the end, the generated images are still not really good. Right? So then what happened was in 2014, there was this PhD student called Dr. Goodfellow in the US who introduced GAN's generative adversarial neural networks as part of his PhD thesis, right? And what this does is that it has a generator and a discriminator based architecture, right? So what it what it wants to do is start from random noise, right? Start from some random Gaussian noise, and then kind of sample that noise until it reaches what it wants to generate. And I've taken the same example over here. It's for the youngest handwritten text data set itself, right? And you can see that this has taken far lesser steps than the previous VAE architecture to arrive at the handwritten text, the final handwritten text, right? And you can also see that the output is much better. It's not actually shown in this visualization over here. But the problem is the training data that you require to train a GAN is far more higher than a VAE. Right? But in terms of the generation output, it was much better. Right? Okay. So in 2017, there was this transformer revolution by Ashish Vaswani and his team from Google Brain, right? And this was from this famous paper called Attention is All You Need. And if you don't know already, transformer is the architecture that ChatGPT uses. Right? Not just ChatGPT, but any LLM-based model that you have today is actually focused on, it's based on this attention mechanism. Right? So what they have is a very similar encoder plus decoder architecture, but they also have something called a self-attention mechanism. Right? So what we'll do is we'll have a look at it from a vision point of view. So there is an image, and what you do is you kind of divide this image into multiple patches, right? And then you have these patches over here, right? So you have these patches, and then you have patch embeddings for each of the patch that you have, right? Now what attention does is that it tries to compare with every single embedding that you have, and it tries to understand which embedding is very important based on that specific embedding list that you have, right? So basically it attends to every single embedding that you have. Every embedding attends to every single embedding that you have. And then in the end it kind of converges and tries to understand which part of the image is kind of linked to the other patch of the same image, right? So in the end, what happens is, so in the end, you have this encoder, and then you have this final MSB, where you classify what exactly is present in that image, right? So classes are nothing but different, let's say, classes, objects that are, let's say, present in that image. And then you can kind of get a score of, or let's say, a probability of all of these classes in that image. Like for example, there is a building over here. So the score for this would, let's say, be 90%, because there is a building for sure in that image. Right? Like for example, there is a bird in the image somewhere over here. Then the score for the bird also would be somewhere close to 80 or 90%. Right? So this is the vision transformer architecture that you have over here. Alright, so now we're kind of getting into image generation, right? So in 2021, there was this model called DALI, which was actually introduced by OpenAI, right? So you can see that this is kind of like a text prompt to image kind of a model. So it takes in a text prompt as an input, and then it generates an image as an output, right? So what this one does is that it again starts with random noise, and it also adds Gaussian noise on top of that component, right? And then you do a denoising step, right? So you kind of remove noise from the noise that you added to arrive at the final image that you have, right? And for each image, you kind of remove the noise in a specific pattern so that you arrive at that final image that it corresponds to the text input that you gave it as an input. Right? So you have a text encoder over here. So you have this text, caption here. A corgi playing a flame-throwing trumpet. Right? That's very unusual, right? So you kind of generate text embeddings using this encoder, and then you kind of process that, and then you have a decoder which kind of generates this image in the end. So this was in 2021. Alright, so let's look at a few prompts that I kind of generated using DALL-E, right? So the prompt is an armchair in the shape of an avocado, right? So this is very unusual, but notice that the model was able to transfer the characteristics, the visual characteristics of an avocado to the armchair, right? So over here. So what it does, or what it did over here, is that the cushion is nothing but the seed which you see within the avocado itself, right? It kind of transferred the visual characteristics in that way. So this is pretty interesting. There's another prompt over here which kind of converts, line drawing into actual images, right? So the prompt is the exact same cat on the top as sketch on the bottom, right? And this is reversible, right? So you can, give this as an input and generate a line drawing, or give a line drawing and generate realistic images, right? So it was able to do that as well. Alright, so in 2022, OpenAI came up with DALL-E 2, right? And now you can see that the quality of the images that were generated also improved a bit compared to the previous DALL-E model, right? So the prompt over here is an astronaut riding a horse in photorealistic style, right? Again, this is very unusual. This is not possible in real life, right? But you can see that the model was able to transfer those visual characteristics into the image that finally was generated. Right? And there's a fun prompt over here. Teddy bears shopping for groceries, photorealistic. Right? So you can see over here. Pretty fun. Alright. So in 2022, Stable Diffusion 2, this model was launched, right? So this is from stability.ai, right? And the architecture looks like this, right? So if you've seen flip-based models, they have two encoders, right? So you have the image and you also have the text prompt. So basically you have the image and then you kind of, let's say, give a context on what exactly that image is, right? So you have an image and then you have a corresponding caption for that image. Right? So you generate embeddings for the image as well as for the text that you have, and then you use that to compare the embeddings, and then you keep updating them. Right? So that is how this model kind of works on the top. Right? So there are some images from the prompts for Stable Diffusion 2. Right? A Pikachu fine dining with a view to the Eiffel Tower. Right? So you can see that the model was able to generate very realistic looking images for such an unusual caption that we have over here. And then an insect robot preparing a delicious meal. Right? Alright. So I have a friend in the US who kind of focuses on professional photography, right? So he has this major $50,000 setup, and kind of a studio setup that focuses on capturing images for models, right? So let's look at a few images that he has shot in the past couple of years, right? So this is an image, right? So you can see that the lighting is really good and the clarity of this image is really good. And this is another image that he shot of this musician over here that is playing the violin. Right? Again, really good depth, also really good emotions that have been conveyed. The colors are really good and the clarity is also really good. This is an outside shot over here in the streets, You can also see the bokeh, the depth of field that you have in the background, as well as really ambient lighting on your face. But these are not real images, right? These are not real images. These images were not shot by my friend who apparently had $50,000 setup, right? So let's look at these images again. Alright, so 2023 and 2024 actually saw the launch of photorealistic image generation models, right? So these are models that can generate images that look undistinguishable, whether they were actually shot using a professional setup or it was generated by just a generative model, right? So the pioneers of this is from Midjourney, right? So Midjourney V5, and it had the ability to generate photorealistic images. And all of the images that I showed previously, the 3 images, were actually generated using Midjourney, right? And obviously they don't want to reveal the architecture of the model, right? So it's kind of secretive. And they had this Discord server-based inference, and it was only based on invites that you get. It was very confined on who could access it and use it. There's another image that was kind of generated using Midjourney. So Stable Diffusion 3 actually launched in 2024, 2025 period, right? But what this one uses is a DIT-based transformer-based architecture. So it's kind of like a diffusion transformer, right? You can probably read the paper and learn more about it, but we will not go into the architecture. Right? But this model is actually open source by stability.ai. So if you've used Hugging Face before, it's like a model repository for ML models. So you can write a couple of lines of Python code to kind of inference or to perform inference using this model. And you can generate photorealistic images on your local machine if it has a GPU, or you can run it on Google Colab using the GPU functionality. So you can also read the paper, but this is an image generated using Stable Diffusion. This is also another photorealistic image generated using Stable Diffusion 3. This open source model that was able to generate really high resolution image. You can see the reflections on her eyeball over here. Right? The iris. You can see the reflections. It's pretty incredible. And just 1 or 2 weeks ago, Google came up with this Nano banana model, right? So this is like one model that can do a lot of these different tasks, right? So it can do text to image, it can do 3D object manipulation, it can do background replacement, it can do this manipulation based on the input image that you have, right? It can also do photo restoration and colorization, right? And it can do a lot of these things in one single model. I have a task for you. So what you can do is pick up either Stable Diffusion 3 or Google Nano Banana, right? I want you to write an inference script that uses this model and generates some image, right? Post it on your LinkedIn and tag me, and I'll kind of comment on your post with my thoughts, right? But the most important thing over here is that you learn how to write the inference code for this model and try to use it for your own projects for different use cases that you can probably think of. So this can be like a start towards that direction. Right? Alright, so now you can use these generative models to do different capabilities. Right? So in painting is one such capability. Right? So you can see over here that you create masks. So basically you're trying to remove ringtones over here and also add different features, right? So just notice this on the right. So this is actually called de-aging, right? It's removing ringtones in real time, and it's actually regenerating those pixel areas from scratch. And this is also called content-aware editing, right? So if you just randomly fill in those pixel areas, it won't look seamless, right? So you need to be aware of the content or context around it to be able to fill it properly. Super resolution is another technique that we use in the medical industry. Right? This is actually an MRI of your human heart beating in real time, right? But the problem is, all of these scanners, MRI scanners, the raw data that you get out of these scanners are not high resolution. So it natively introduces a little bit of noise into the raw data that you get. So super resolution is a technique that you can apply on these data points to kind of smoothen out the data that you have. So it's kind of like a pre-processing step before you use it for some kind of analysis. Right? So you can enhance all of these low resolution images, and you can get really good outputs out of that. Right? So just notice this. So it's like applying super resolution on the same image multiple times until it gets really good in terms of clarity. This is another technique specifically for surveillance applications, right? So let's say that there was a thief who kind of stole something and then ran away, but then the CCTV camera was not able to kind of capture his number plate because he was really fast. The car moved really fast, and then the camera's frame rate could not match. Right? So you can actually use deep learning techniques to kind of find the actual number plate for that car which moves really fast. Right? So it's really helpful for surveillance and forensics-based use cases. Mostly for data retrieval. Right? So let's talk a little bit about ethical considerations, because now we know that this tech is really capable. Right? We know that it's so powerful that if it gets into the wrong hands, it can be misused very easily. Right? So you have two videos. Which one do you think is fake and which one is real? So people that say the left one is real, raise your hands. Okay. People that say the left one is fake, raise your hand. Okay. So this is actually real, and this is fake. Right? So that is how realistic all of these models can, output data. So these are not just image generation models; these are video generation models, right? So it's like image generation models on steroids, because video is a sequence of images, right? So all of these things can be used to spread misleading content on social media. Right? So that is something that we need to be very careful about. Okay. The second thing is privacy and consent. Right? So all of these models, right, they need really large amount of data to be trained. Right? So in fact, all of these, stable diffusion or video generation models, they need terabyte scale data to get this kind of an output that you see over here. But all of these companies, where are they getting all of this data from? Right? So that is one thing that you kind of need to think about. And the second thing is, all of this data that you have, all of the sensitive data, or all the private data that you have, is it really private? Right? So all of your Google Drives, is it really private? Right? Because it's free storage. And all of your Google Photos, is it really, private? So there's a need for consent over here. And in the end, who's the owner of the data? Right? Is it you because you own the phone, but the data is not stored on your phone? Right? So that is something that also needs to be considered. The third thing is bias and fairness. Right? So models can inherit biases from the training data. Like for example, let's say that I have a data set of cats and dogs. Right? So let's say for cats, I had 100 images, and then for dogs, I had 10 images. Right? Now, even if I ask it to, generate a dog, it will look very similar to a cat because there's a bias in the data itself. Right? It won't look good. It will look really bad. Trust me, I've seen it. So the data set needs to be balanced, right? And also the generated content may be biased, right? So you need to be able to balance the data set that you have, the training data set that you have, to be able to get a state-of-the-art model in the end that generates really good images. So the fourth thing is authenticity and trust, right? We saw that it's really difficult to differentiate between real and generated content. So there needs to be a little bit of compliance that kind of assists normal people to be able to classify real versus generated, right? And then there is this major implication in journalism and evidence, right? Because I can create false evidence for someone and then prove them wrong. So that shouldn't be a case, and it wouldn't be justified. So that is an ethical consideration. Alright, so that was kind of like an overview of image generation using generative AI, right? And then I'm opening the session now for Q&A. So if you have any questions, please feel free to ask. And I think we can also give a mic probably.
Hi sir. So if we talk about image generation, so how do we make sure that the images that are being generated, they are not of the real people? We have a lot of images in our training data set, which would obviously in the first hand be of people who are they exist. So how do we make sure that the images that we are generating and using for our usage are not of someone who already exists? So this is a major thing because most of us use images that are generated by the LLMs that these companies use. So how do they tackle this problem?
So basically, you should not train the model with raw data itself, but there are a lot of these steps in terms of pre-processing that you run on your data set, right? So one thing is pre-training a model, right? So all of these really large models are already pre-trained on let's say billions of images from the internet or from different data sources that you have, right? And then what you can do is you can fine-tune this pre-trained model on your custom data, right? And this is where you bring in that control. So you have a really small data set, which is specific for your use case, right? And you bring in the control in your small data set itself because the data set itself is so small that you can pre-process it as much as possible, right? But when it's terabytes or petabytes scale data, it's not possible. Right? So you can adjust the weights dynamically with the fine-tuned data set, custom data set that you have, and then fine-tune the model. So this will help you to mitigate that issue. Yep. Anyone else?
So in last you saw.
Yep.
So in last you saw one slide
Yep.
bias and fairness.
Yep.
So when it comes to the medical data set, yes, we are applying the transformers and all. And let's suppose we have a disease data set, we are applying a classification task. But when it comes to the clinician, they said no. So So would you prefer the transformer and all over the traditional techniques? If yes, then why? Mostly medical data set, the clinician would not prefer these things. So why?
Yeah, so one thing is, so there are two answers to your question. So the first thing is explainable AI, right? So basically it's not that, hey, if this model said that this is the disease that is present in that specific scan, it is that disease that is present in the scan. It's not like that. The AI also needs to be explainable based on how it arrived at that conclusion, right? So what characteristics did it consider to say that, hey, this is malignant or not, right? Or benign or malignant, right? Second thing is human in the loop, right? So usually in clinical workflows, you don't completely trust an AI model, at least as of now, right? So after you get an output from the model, and you also have, let's say, context of how or what are the considerations the model did to arrive at that conclusion, and then the final call is always the doctor that takes during the treatment, right? So it's kind of like a human in the loop or doctor in the loop process that we follow.
Thank you.
Yep.
So I have a question. Let's say we were to train an AI model to detect if an image is AI generated or not. So what would the AI model that you're training look for in an image in order to be able to distinguish between a real and a AI generated image?
Yeah, that's a good question. So I'll go back a couple of slides. So when you compare these two videos, you can see that there are a little bit of dilations over here around his eyes. I don't know if you can notice it over here on the projector, but if you look at it on a laptop screen, it's much more evident, right? Second thing is the structure is not maintained, 100%. Right? The structure of the subject keeps changing, so that itself is a pattern. Second thing is there are a lot of deformities in different characteristics of that subject. Right? So those are the kind of patterns that we look for. But what happens is if you want to train a model for, let's say, a true versus generative image, then the model needs to be really deep because it needs to be able to capture all of these underlying patterns. Right? But these are the characteristics you generally look for. Yep.
Hello sir, my question is, are image editing and image processing the same thing or different?
Oh, it's different, right? So image processing and image generation. Is that what you asked?
Yeah.
Yeah. So I think image processing is basically manipulating the image, input image that you have to gain useful information out of it. But image generation is kind of generating an image itself from scratch based on some text prompt or let's say different modalities. Right? So what we explored is that okay, so these are some final thoughts and suggestions. So I think now you kind of have like a foundational theoretical knowledge of all of these models, and we also kind of explored all of these different image generation models and their capabilities in all of these years, right? And we also explored few ethical considerations that you need to keep in mind while using all of this cutting edge tech. So all of you are ready to explore generative AI. So the thing is, there is new innovation in this field every single day. And I was just speaking with a couple of students over here, and I told them that if you sleep today and wake up tomorrow, there are like 5 to 10 new generative AI papers that are launched. So that's how hot this field is, right? So to be able to, catch up with what is happening and what needs to be done in the future, so that is only possible if you read all of these research papers, right? So you can look at, platforms like Archive, papers with code, and also on Twitter, people keep sharing, cutting-edge papers, right? You can also follow a lot of, profs from, international universities who keep publishing all of these papers, right? But you should make it a practice that you read all of these research papers so that you know the different architectures and how it kind of contributes towards the kind of images that it can generate and its capabilities. So, and also build applications that solve real-world problems. Don't build cat versus dog model, right? Build applications or build models that actually solve some real-world problem, so that you can kind of publish it, open source it on GitHub, and then that can actually help you in the future for a lot of these opportunities. Right? And then also be happy while you're doing this, right? Because sometimes if you go in really deep into all of this deep tech, you kind of feel lost. But take it easy and try to learn as much as possible. So that's it for me. There's a QR code over here which you can scan. So if you are working on exciting projects, or if you need help with your research, you can reach out to me. Right? You can Google my name. It's Pranav Durai, and you can reach out on GitHub or on LinkedIn, and I'll try my best to help you out on different research paths, right? But also, if you had any other doubts or clarifications, you can put it up on this form, and I'll reply to every single response that I get in the form. I'll just leave it open over here for some time.